Lecture 5. In this lecture, we are going to learn the basic elements of topology. We are going to speak about the open sets and closed sets and the idea of compactness. The modern set theory has been introduced by the Cantor in 1817. And my advice to you is to understand these ideas, since all of them are very geometric. Each time you should draw mental image that depict all of these ideas so you can get the feel for the definitions. If you don't have associated picture, it's very hard to remember all definitions. Usually in our studies we want to have the points, and these points are very important. The thing you may notice that every point in interval AB has the feature that if we take any point x, then every small interval, there exists a small interval such that the interval itself is in I. In literature, you may see that for positive number c or epsilon, usually denoted by epsilon, then this set is called neighborhood. It's called the neighborhood of x. Thus, each point in AB in the interval a from b possesses a neighborhood, and many of them, this neighborhood, are inside the set. Let's define one of the important points that we use in our analysis. If we have set E, then for every point x in A, then the point x in E is called an interior point of set E if there exists some neighborhood of x that is inside E. You can see that any interval AB has infinitely many points, and it turns out that for open interval AB, all points are interior. To see that what kind of points are not interior, let's consider the natural numbers. So this is our real line, and we have 1, 2, 3, 4, and etc. You can see that for each point in natural numbers, if we take epsilon small interval, then it does not contain in natural numbers. Those kind of points called the isolated points. So let's give one more definition. Again, we have set E of real numbers, and if x in E and such that we have, let's say, epsilon neighborhood of x intersecting for E is equal x, then this point called the isolated point. If there exists epsilon greater than 0, we have the following, then it's called isolated point. Usually we are interested in points that are not isolated. We define, if we again have set E, any point x is said to be an accumulation point of E if for all epsilon greater than 0, the intersection of the neighborhood of x and this should be epsilon, neighborhood of x and E contains infinite many points. In other words, if we are in real line, the intersection is interval, then the point is accumulation point. The other interesting points are called the boundary point. To see the intuition, suppose we have A and B. Then this interval, for this interval, A, B are kind of the edge of these intervals, and A and B in this case are the boundaries. So let's give the formal definition of boundary points. Again, we have E, and X is said to be a boundary point of set E if for epsilon greater than 0 the neighborhood of X contains at least one point of E and also at least one point that does not belong to E. In our case, if we like the interval AB, so if you take epsilon, you see that everything whatever is left A does not belong to the interval AB, but whatever is in the right of A, it is inside the interval. So A in this case is boundary point. Now let's illustrate the previous definition using some example. We want to find the interior, isolated, and accumulation point for the following sets. So we have interval AB. You can see that all points of inside the interval are the interiors. It's very easy to see whatever point we take, then we always can find some small epsilon such that this interval is such that the neighborhood of X is inside AB. To answer that, interior of AB is AB itself. Let's find the isolated points. Isolated points, remember, isolated points are those points such that if we intersect neighborhood with itself, then we get 1 point. You can see that there is no isolated point. So the isolated point set of isolated points is empty set. To find accumulation point, we go back to definition of accumulation points, and it says that X is an accumulation point. If we intersect with the set, then it contains infinite many points. You can see that for any point X we take and we intersect it with AB, we get the neighborhood itself, and which is interval that contains infinite points. So accumulation point of AB is AB itself. The last one are the boundary points, and boundary points are the points for all epsilon greater than 0, the neighborhood of X has points, one from the set AB, the other complement of the set AB. The thing is, we find that the interior of AB is itself. So whatever point we take inside X, it cannot be boundary point, since there exists at least some epsilon for which it contains inside the AB. But if we look on the A and B itself, whatever epsilon we take, there exists one point is in left, and that is outside of interval AB. The other point is inside AB. So the boundary points of interval AB is A and B. Now let's do other example. Suppose set of natural numbers. Remember that those are the numbers 1, 2, 3, and etc. Now let's find the interior point. To find the interior point, it means that the neighborhood of the point should be inside this set. But if we take the neighborhood of 1, let's say epsilon neighborhood, we see that those points are outside the natural numbers. Therefore, the interior of natural numbers is empty set. Now let's see on isolated points. Isolated points are points if we take some epsilon neighborhood and intersect with the set, it gives the same point. In our case, you can see that whatever point we take and intersect with the natural numbers, which are in our case, let's be reds, then the intersection gives red itself. So the only point this intersect is red, the natural number itself. Thus, the isolated point of a set of natural numbers is itself, accumulation points. Remember the definition. Accumulation point says if we take neighborhood and intersect with A, then intersection should contain infinitely many points. But if we take neighborhood and intersect, we get 1 point. So accumulation point is an empty set. And the boundary point, if we take again neighborhood, 1 point is inside the set, then the other is outside the set. And we can see that no boundary point for the set of natural numbers. Now let's talk about topology of sets. Topology is a branch of mathematics and is fundamental to an understanding of many areas of mathematics. Now we will describe open and closed sets on real line and give precise description of what kind of objects they are. Let's start by defining closed sets. Suppose E is a set of real numbers. So we say that E is closed if every limit point of E belongs to E. Recall that a point X is called the limit point or accumulation point if for all epsilon greater than 0, intersection of neighborhood of X with E is infinite. Therefore, the set is closed if it has all these limit points. For example, in this case, if we are dealing, let's say, with the closed set, dangerous points here are the boundary points. So if they are inside the set, since whatever epsilon we take, then it will contain inside the set. In general, set E is not closed if we can find some accumulation point of E that does not belong to E. That is, for example, for the open interval AB, consider point A. A is an accumulation point since whatever epsilon we take, the intersection with interval AB is infinite. But A does not belong to interval AB. So AB is not closed. Open interval AB is not closed. On other hand, if you consider closed set, so in this case AB belongs to AB is closed, then inside points of any point inside A, B is of course accumulation point, but the edges of AB interval, which are the points A and B, they are also accumulation points, but in this case AB does belong to interval. So closed interval AB is a closed set. The other interesting thing, you may note that if we want to make a set closed, what we need to do, we need to add the missing accumulation points. And the thing is, if a set does not have accumulation point, it should be closed, since there is no point that needs to be added. Let's give one more definition. Suppose we have set E, and let's A prime be all limit or accumulation points. Then the set, which is equal union of set E itself and its accumulation point, called closure. Of the set E. Of course, closure is a closed set, and the set is closed if and only if the closure is equal set itself. Now let's do a couple of examples. Let's consider the set of natural numbers. As you remember from the previous example, the natural number limit points of natural numbers is empty set. Therefore, natural number is closed since it does not have any accumulation point and there are no points we can add. The other example we can do is rational numbers. So our example is all rational numbers, and accumulation points of rational numbers is a real line, but irrational numbers does not in Q. Therefore, Q is not closed. Now it's a good time to define open sets. Suppose E is a set of real numbers. Then set E is open if every point of E is also an interior point. In other words, if for all points x in E there exists some neighborhood such that the neighborhood is inside E. From here it's immediate that an open set cannot contain any of its boundary points. Since remember, the definition of boundary point is the point is boundary, y let's say is boundary point if any neighborhood, for every neighborhood, there are points that belong to E, and also there are points that belongs to the complement of E. Therefore, a set is not open if it contains points which are not interior. Therefore, if we get rid of those points, then we will get a smaller set composed entirely of the interior points. Let's define what are these points are. Again, we have set T of real numbers. Then the set interior E is the set of all interior points. Let's do one more example. Suppose the open interval AB. Then remember that we say that interior points of AB is AB itself. So the interior, let's denote this as I. Then interior of I is AB itself, which is I, and I is an open set. If we consider the closed interval AB, so interior of I is an open interval AB. So to see this, suppose this is our interval AB. Then remember that AB, they are boundary points. If we get rid of these points, if we exclude them, we end up with the interior points. Consider the natural numbers. As we said that natural numbers is a closed set, and natural numbers does not have interior points. For rational numbers are not open. So as we said that irrational numbers are dense. It means whatever epsilon we take, there in this neighborhood of epsilon, there are points that are irrational. It means there are points that does not belong to Q. Therefore, Q is not open. So we end up saying that for rational numbers are not closed and are not open either. Therefore, if set is not open, it does not mean it should be closed, and vice versa. If it's closed, it does not mean that it should be open. The following theorem examines the relationship between open and closed set. It says if you have set E of real numbers and set B is its complement, then A is open if and only if B is closed. Now let's give a couple of properties of open and closed set without proving this. So try to have a mental picture of these properties. Open sets have the following properties. First, empty set and R are open, and as well they are closed. So those are the only sets that are open and are also closed. Any intersection of a finite number of open sets is open. So interesting point here is why we need it to be finite. What if it's infinite? In this case, we can give example. Suppose we are dealing with open sets. So this is a family of open sets indexed by n. The examples of these sets are, let's say, A1 is minus 1, 1, A2 is minus 1 half to 1 half, and etc. You can see that the thing we learned is minus 1 n goes to 0 as n goes to infinity, and the same way 1n goes to 0 as n goes to infinity. Therefore, in goes to 0. So therefore, if we are looking on the intersection of infinite number of set, so remember, intersection is the intersection of the sets are the points that are common, and the only point that are common is the only point that is common is 0, but 0 is closed. Therefore, we get that we can have the infinite number of intersection of open sets but end up having a closed set. That's why finite is here is very important. Union of collection of open sets is open. In this case, if AI is open, then any union of open sets should be open. To have some mental picture, here what we are dealing. Suppose we have the following sets, so they can intersect or may not, it doesn't matter in our context. So all these sets are open. If we take if we take union of them, we end up having open set. And the fourth one, which comes from the theorem, is that the complement of an open set is closed. Now let's give a couple of more examples about the closed set. Any union of finite number of closed sets is closed. So again, the finite here is very important. You may come up with the example where you take the union of infinite number of closed set, but ending up having a open set. However, the intersection of any closed set where A is closed for all I, so the intersection is closed. Again, this is what we have. So those are the points that include their boundaries. If we take intersection of them, it's always closed set. Even if we end up having empty sets, remember that empty set is closed. And the last property is that the complement of a closed set is open, which comes from the theorem. Complement of a closed set is open. The next point I'm going to speak about is compactness. To give motivation about compactness, think about this way. The compactness helps us to generalize our assumptions. Let's define what is compactness. Set E is compact if every sequence in E has a subsequence that converge to a limit that is also in E. There are different definitions of the compactness using covering property, but in our context we will not go over there, but remember that there are also other definitions, and there is a theorem which says that they are equivalent. The important theorem about compactness is something which called Hain-Borel theorem, and it said that set is compact if and only if it is closed and bounded. Now let's give example. We want to decide which of the following sets are compact. Rational numbers. Based on the Hain-Borel theorem, we need two things. It should be closed and it should be bounded. As we said that Q is not closed, therefore it's not compact. The second set is a closed interval AB. AB is closed, so this is check, and AB is also bounded since we can find number which is greater than B. This is also check. Therefore, from theorem, AB is compact.